So, quick review. What is kinetics focus? What is what questions does kinetics seek to ask? Okay, how fast and what are the steps? Okay. Then we talked about something known as the collision theory, correct?
Yeah.
What is the collision theory?
It's got to collide first of all.
And if you have all of those things, then what? What happens? A reaction can happen. Yep. Okay. So what you have is you could have a collision and it not cause a reaction. Okay. And we're going to kind of elaborate on that and talk about that a little bit more as we progress. We also talked about the difference between favorability and spontaneity. What was the main difference?
Spontaneity is like it will happen. Favorable is it can happen.
Yeah, essentially, like from a favorability standpoint, it's saying it's likely to happen from an energy and entropy standpoint, but it's not the only thing that determines it will happen. Okay? If you say something is spontaneous, as soon as they come into contact, it will happen. Now, does that mean it will happen fast? No. Depends. Okay, I gave you 3 examples. Diamond breaking back up or breaking down back into carbon happens spontaneously, but it's so slow that it's going to take a long time for you actually to see it. All right, so we're going to start off by talking about activation energy, and I think I'm hoping I have some graphs, energy graphs coming up here. But all right. So, even though a specific reaction may be spontaneous, it will not proceed rapidly unless it overcomes an initial barrier, which we would call activation energy. It's the energy needed to jumpstart a reaction. The reason why gas does not react by itself is because of this. What do we do to get gas to start burning? Light it on fire. Yes, kind of.
Give it energy.
Yeah, give it energy. Okay? And usually in the form of a spark. You're not wrong, light it on fire. But what do you do to start lighting it on fire? You give it a spark or an input of energy. It's not like you just throw fire on it.
No.
Alright. Now, if we have a lower activation energy, the reaction will probably occur faster and will probably occur much easier. So let me show you what I think the next slide will be. I'm just going to come back to this. Okay? So I know this is a really excessive activation energy. Okay? First off, is this thermodynamically favorable from an enthalpy standpoint?
Enthalpy standpoint? No.
No, because he goes from
Yes.
Yes, because he goes from
Yes.
Yeah.
What has higher energy? My beginning or my ending?
And so
Yes,
it's
no.
exothermic, so it is favorable.
Right?
It's not spontaneous, though.
You're right, it's not spontaneous. I didn't say is it spontaneous. What did I say? Is it thermodynamically favorable from an energy standpoint? Beginning and ending, right? Thermodynamics is path independent. Doesn't matter this, just beginning and ending. From a beginning and ending standpoint, are you gaining energy or losing energy?
Losing it.
You're losing energy. Okay? Now, the path tells us that we have to overcome this little hump. I mean, this is not a little hump, but this hump, which will be from the energy of your reactants to the top of your hump, is known as the activation energy. If you do not surmount or overcome that activation energy, will you ever get to your products? That makes sense? Unless the ball rolls up and over the activation energy, are you going to be able to get down to the products? No. Okay? So, what the activation energy is a lot of times due to the steps of a particular reaction, you need to input a lot of energy to get over that first step. Okay, because remember, we said that a lot of times a reaction doesn't occur in one step. There are multiple steps. Do you remember Hess's law where we manipulated the steps and we flipped the equation and we multiplied by coefficients? Do you remember that? Well, if that first step takes a lot of energy and is endothermic, that's why we have an activation energy. It doesn't matter if the second and third steps are really fast. If you can't get past the first step, are you ever going to get to the second and third steps? No. So, a lot of times, a step will require a lot of energy, and so that's why we have to input a certain amount of energy to get over what's called this activation or energy barrier. It's the same thing when you burn gas in any flammable object. It doesn't just miraculously go poof. You have to give it an input of energy, a kickstart. Okay? When Grandma wakes up in the morning, kickstart. Ah, okay.
All right.
Sorry. Okay, activated complex. Okay? This is what's called a transitional structure between the reactants and the products. It is the top of the hump, or the highest point of your activation energy. Okay? Called the activated complex. It has a name. Now notice it's called a transitional structure. Here's another really important thing about the activated complex. It's really highly energetic. So if it's really highly energetic, it's probably, right? High energy means low stability. Okay? So what you have, and during the activation complex, is you're in the process of breaking old bonds, but also in the process of forming new bonds. So it's a really high energy transition state. So let me kind of show you what that looks like. Here on the graph. First we said the energy from the reactants to the top of the hump is called what? Activation energy. The top of the hump is called the transitional state, or activated complex. Okay? The activated complex is when you're in the process, you haven't completely broke your reactant bonds, but you haven't also completely formed your product bonds. So it's really like in the process of forming and breaking bonds, and you can imagine that's going to be a very short-lived, high-energy, unstable state. Yeah, on the graph, how do you know it's high energy? It's at the top. It's the highest energy point of your particular reaction. It's the shortest lived, okay? Doesn't last very long, very unstable, okay, because you're in the process of breaking and forming bonds at the same time. Not stable, okay? So two things we've talked about today. Activation energy. Energy from reactants to the top of your pump is called the activation energy. The amount of energy needed to jumpstart or cause your reaction to occur. What is the difference in energy from reactants to products called? I didn't say today, but what's it called?
Change in age.
Change in age.
Oh.
Praise God! Isn't that products minus reactants? Okay, so we've got our change in energy from a reactants, products minus reactants standpoint. So this is the thermodynamics portion of the theorem. This is the thermodynamics portion. This is the what portion? I heard it. Kinetics. So what you have? Path independent. Path dependent. Okay? Kinetics deals with the path. Thermodynamics just deals with the beginning and the ending. Put them together, you have a big picture of what a chemical reaction is needed and what it looks like. Okay? At the top of the hump, what is the top of the hump called?
Transitional structure, or.
It's called the activated complex. It is a transitional structure. It's the transition from reactants to products, where you haven't completely broken product or reactant bonds, but you haven't completely formed product bonds. So it's your high energy, unstable state. Right. All right, that's what there. Okay. Just looking at this quickly. Now, none of these are spontaneous. Which one is the closest to being spontaneous? Which one is the furthest from being spontaneous? D. Okay? Which one has the greatest, is the most thermodynamically favorable? A. Everybody understanding what the questions I'm asking and how we're getting the answers? This one's the most likely to be, or the closest to being spontaneous because it has the smallest hump. Okay? This one's the least likely to be spontaneous. Not only is it very endothermic, but it also has an additional hump on top of it. And this one's the most thermodynamically favorable because it has the biggest energy change from the reactants to the products in a releasing energy fashion. Right? Reactants have higher energy than products, so energy is going to be released from a product minus reactant standpoint, correct? Okay. All right. I probably could have thrown this in tomorrow's lesson, but it just kind of sits here by itself. We're going to talk tomorrow about reaction rates, or how fast your reactants are going to transfer into your products. The faster the reactants turn into products, the higher reaction rate you have. The slower, the smaller reaction rate you have. Okay, usually expressed, what's this? No?
Would it be polarity?
Molarity. Which molarity was a what unit?
They didn't have a unit.
Molarity was the unit. What type of unit is it? It is a concentration unit. What were the other three concentration units? Molality,
Percent by volume.
percent mass, percent volume. Okay? So, it would make sense that I want to know the concentration change of my reactants to my products if I'm trying to figure out the rate or how fast the reaction is reacting. And we will spend a ton of time with this tomorrow. That's why I think it's thrown in there because I'm just going to talk about a few things that affect the rate. First off, rate means what?
The speed at which something can.
How fast the speed. All right. There are 5 things that affect rate. Very first thing is simply the chemical nature. Some things react faster with other things just by their sheer chemical nature. Can we affect that at all?
No.
Yeah. Okay.
I'm falling asleep.
Stand up. Walk around.
Put your hand
I just feel
down.
sweaty.
Yeah, good idea. Second thing, concentration. Now, I'm going to ask you a few questions about the rest of these. Okay? I'm going to ask you, based on the collision theory, why would this make it react faster? Yes. Is everybody here? Morgan. If you have a higher concentration, aren't you going to have a higher likelihood that those things are going to collide? If you have more collisions, more of those collisions are going to be properly oriented, right? Okay? So, if you increase the concentration of a particular reactants, you are going to see it react faster because you have more collisions. Next one. Why would an increase in temperature cause the rate of reaction to increase?
The
Molecules
molecules,
faster, cause
they
more.
move faster, more collision.
It's really twofold, right? One, you're going to have more collisions because they're moving a lot faster. And 2, they're going to be hitting each other with a greater
Force.
force speed, higher energy. Okay? if they hit each other with a higher speed or greater force, more energy, they're likely to surmount what? What did we talk about at the beginning of this class that they have to surmount? Overcome.
The hump.
The hump. What's that hump called?
Activation energy.
Complex.
Okay, the top of it's called the
Okay.
complex, but the hump itself is the what?
Activation energy.
Activation energy. Remember, if we cannot overcome the activation energy, is the reaction going to occur?
No.
So if we can speed them up, give it more energy, give it a kickstart, a spark, is it more likely to occur and occur faster?
Sure.
Absolutely.
Of course.
Okay? Surface area. Do you think an increase in surface area or a decrease in
Increase in surface area. Increase in surface. What?
Someone explain why you said
Wait,
one
are we
versus
talking
the other.
about like one
Increase
of the
surface area
surface
'cause that means
areas
a lot of
on
small
another,
particles.
or the whole thing
Say that again?
surface area? The whole thing surface
The
area,
particles.
or
The particle surface area.
the
Increase.
something hitting something?
It's increase in surface area.
Okay, why is it an increase in surface
Because
area?
then you have more smaller particles to collide.
Isn't the whole idea for increasing the rate have to do with the collision theory?
Yeah, but I'm saying,
You were right.
is it like two liquids in one that surface area, or is it something surface area hitting another
So-
thing?
Do you guys understand what I'm
What,
saying?
I think he's asking, is it like the surface area of the liquid or something, or is it the surface area of the
Is it the surface area of the thing being hit or the thing hitting? Is that what you're saying?
Where'd you get a liquid from?
Is it one surface area or two surface areas?
Doesn't an object only have one surface area?
No!
Alright, I've got a box here. How many surface areas does it have?
No!
One.
That's just one reactor.
Yeah, you noticed?
You want both the thing that's colliding and the thing that's doing the colliding to have as much surface area as possible.
Yeah.
Yeah, but I'm saying, is it?
Gabe, you just answered your question. That's what you're asking, isn't it?
It's hard.
Oh, it's
That's so hard to interpret sometimes.
I understand
You're so-
why.
I understand what you're asking. Like, is it
No, why
like?
don't you tell them?
Because I can't word it. I can't
Exactly.
word it any other way than what you say.
Something hitting something.
Yeah.
Good.
Oh, the surface area of two things. The surface area that touches
We
each
want the
other.
bigger.
That's what I said.
Or
I said
versus the surface
I answered that question. I said, so you're saying that if there's particles colliding with this, which one it needs to have a higher surface area? Is that what you're asking?
No.
Like,
I'm saying.
okay.
Alright, let me see.
If a
Let me
box
see.
touches the side of a box,
If
versus
there's
tiny
two-
particles.
If there's two substances already in a object, or if it's two objects about to collide.
Oh, I see what you're saying. Because if they're in something, then
You would
there's
want-
blood, you
So
want
you
You want
something
smaller
to
surface area if they're
collide more.
both in
That would be smaller volume.
Yeah, I know, but
No.
that's
Yes.
That's-
Yes.
Hey,
here.
Because inside here, there's a particle in here. This particle only has one surface area.
No.
Yes.
I'm talking about.
Yes.
I'm talking about in this object.
Yes. Tell me yes.
No. Okay, so let me describe this. Would you rather put two substances, let's say two liquids, would you rather put two liquids in a, like,
Big box or a little box?
no, a, like, more surface area box? Way down. Would you rather put them
Forget
in a
about
ball?
the container. There's
Oh,
no
you're
container.
saying-
Yeah.
Would you rather put two particles in a square or two particles in a circle? Is that what you're saying?
No, like this.
Oh my goodness!
No, it's not, it's almost there, it's almost there. Let's say you have a trough, okay? A trough.
This is going on the book.
So the two liquids are only gonna have this much. Would you rather do that, or would you rather put them in a container like this with the same amount of volume and put them in there? Here he said now. Hey. See what I'm saying?
I feel dumber now.
See what I'm saying though?
No.
Each,
Are we talking liquids?
Yeah.
I don't think it
they have the
matters.
same surface area. If it's the same amount you put in each.
I don't know, but he's saying
No.
they would collide.
or both.
They're
You're
in
saying
the
they're in
zone,
this, they would collide more?
Yeah.
Yes, they would
Yeah.
fly more because they.
Bouncing off the walls more.
Oh, like
That's not
spread it. Oh, like
affecting
the.
surface
Yeah,
area.
see?
Yeah.
It only took 9 minutes.
That was 2. It was 07 when I started talking. That was not 2 minutes.
It's
It
3.
wasn't
Yeah,
nine,
that's
though.
Did that confuse you more?
No.
Well, actually, which one were you talking about?
The surface area of the particle.
I'm talking about if you have two things colliding, you want those two things to have as much surface area
Like the
exposed
salt
as
cube.
possible.
Sorry.
Yeah, so like, I want, if I'm trying to, in order to dissolve salt, okay, or let me say sugar, it might be a better example. In order to dissolve sugar, I want as much sugar surface area exposed so that the water can collide with the sugar. Okay, so it would be best to have it as granule sugar versus cubed sugar. Does that make sense? Okay.
We have a lot.
Second, next thing, catalyst.
Increase rates.
Okay? So what a catalyst does
It makes
is
it
makes it faster without affecting anything else. I think catalysts are one of the coolest things God ever created because they do nothing but speed things up. And if we didn't have them, our bodies would fail to even exist. Almost every chemical process in your human body is catalyzed by a biological enzyme.
It's a word.
Okay, if you ever take biochemistry, Lord help us if you guys do, because biochemistry is hard. I got a C in that class, it was hard class. It was really fun. But you learn about the chemical processes in the body, and they are so complex. Like the citric acid cycle has like 12 different reactions, and then like 12 different really complicated enzymes that catalyze each of those reactions. And it's just a small portion of how your body uses energy. It's phenomenal. Then you talk about the electron transport chain. It's cool stuff. All right. So the question you might be asking is, a catalyst speeds up a reaction. How does it speed up a reaction? Okay. So we know that that's its main function. We know it does nothing else. It doesn't get used up, doesn't affect doesn't affect the change in H, change in S, the change in G, doesn't affect anything else but speed it up or make it faster. And the way that it does it is by lowering the activation energy. So most of the time what a catalyst will do, will grab a reactant that wants to be reacted and it will orient it so that every collision is an effective collision. That's the most common type of catalyst, where a catalyst will come in and it'll grab on and hold on to a particular reactant that wants to be reacted, and it will grab on so that the part that needs to be collided with is exposed. That makes sense? So the only way, if you're going to collide with it, the only way you're going to collide with it is in the right, proper oriented way. That's pretty cool. And then that's not the only type of catalyst, but that's the main type of catalyst, which we'll talk about here in a second. That's the lock and key model, where, like I said, a catalyst will grab and orient a reactant, so therefore it will lower the activation energy. And guys, if we lower the activation energy, does it need as much force and as much energy for the reaction to occur? No. It's going to happen a lot quicker and a lot more likely if that's the case, right?
So the complex is the one on the top, and then the energy is the space between the start and.
Yes. So if I have a hump, or if I have an energy curve that looks like this, okay? Here to here is your activation energy. This is your activated complex. And products minus reactants is your what? That make sense?
Yep.
I could have it look like this. Endothermic.
Oh.
This, change in H, products minus reactants. This is my activation energy. And at the top of the hump is my transitional state known as the what? Activated
Why
complex.
did the hump end so abruptly?
Because I can't draw very well. Alright, so I think I've kind of already talked about this, right? And I would use the word equilibrium, but we haven't really talked about the equilibrium chapter much. So all I will say is a catalyst gets it to equilibrium quicker, it doesn't change where the equilibrium lies. Okay? And I know that probably doesn't make a ton of sense for you, but it speeds up the process, but doesn't change the end point. Okay? It doesn't change where the products and reactants will end, or what the concentration of your products and reactants will be at the end. Okay? So another thing that's really important. We'll talk about this more in next chapter when we talk about equilibrium. That there is a reversible reaction. All reactions, almost all reactions, are reversible, which means that they go in the forward direction and they go in the reverse direction. So if you add a catalyst, it will increase both the forward reaction and the reverse reaction equally. Right? And like I said earlier, since a catalyst doesn't change anything but increase the rate, the change in H, change in S, change in G all stay the same. And there are two types of catalysts. Oops. Homo and hetero. We should know what homo and hetero mean.
Same.
Okay, homo means same, hetero meaning different. A homogeneous catalyst is in the same state or same phase as the reacting molecule. So remember how I said it comes in and grabs? Okay, if it's homogeneous, it would be a liquid grabbing another liquid, or a solid grabbing another solid, or a gas grabbing another gas. Okay? A heterogeneous would be like a gas adhering to a solid catalyst. Different phases. Okay? Homogeneous, the catalyst and the reactant that it's trying to properly orient are the same phase. And if it's heterogeneous, the catalyst and the reacting molecule that it's orienting are different phases. The most common example of a heterogeneous catalyst is a lot of times solid metals are used as a catalyst. So a gas molecule will come and hit the surface of a solid, and that solid will grab a hold of it and orient it and allow the molecules to collide better. Okay, and why? How? When I say collide better, what am I referring to?
More energy and line.
Usually it doesn't change the energy, it changes the orientation. So it orients it. So for example, if I had a bunch of gas molecules in some chamber, and at the bottom of it, I had some solid catalyst. This comes down and hits this. Well, it orients it so that another one comes down and hits it perfectly oriented, causing a reaction to occur. Okay, that would be an example of a heterogeneous. The solid surface would be your catalyst, and the gas would be your reacting molecules. Because if these guys hit, does this mean that any time these guys hit without the use of a catalyst, does that mean they will react? Well, it could. But you could also have a collision that's not what? Properly oriented. So the use of a catalyst is to properly orient it so that if they do hit, and when they do hit, it will react. You guys already know that enzymes are biological catalysts, right? No? Biology?
We didn't really.
That was
we didn't-
last year.
Yeah.
Really? I mean, that's like a huge part of biology.
We
You know what I'm
kind
talking
of
about?
talked about it, but not really.
Okay, so
We just said that.
a catalyst, we said, speeds up the rate of reaction. A enzyme is a biological catalyst. So the catalysts in our body are called enzymes. Does that make sense?
Yeah.
Last thing, inhibitors. These are actually pretty cool. They do exactly what they're called. Inhibit. What do you think they inhibit?
Everything.
A catalyst. Okay? So usually if you have a catalyst that you do not want, you will put in an inhibitor. What that inhibitor will do will go in and will either trick or just replace the spot that the reactant would be attached to. So for example, if I had this catalyst here and I didn't want it here, I would put an inhibitor that would come in and fill its spot so that it doesn't doesn't even grab onto the reactant that I don't want to touch. Okay, so I'm trying to think of a common use for an inhibitor. Can't think of a situation. I'm trying to think of like antibodies, but that's not quite the same thing. Inhibitor. Anyways. I think this is the last one, right? Last, all right.
So you know how Bryce was saying?
Thank you.
I was kind of like, oh no, a bunch of this on